This is Swarfcast. I'm Noah Graff. I am very honored to have George Konidaris, co-founder of Real Time Robotics and professor of computer science at Brown University. He's also the director of the Intelligent Robot Lab at Brown. Welcome back to the show, George.
Thank you, Noah. It's a great pleasure to be here. Really wonderful to see you again and to get to hang out.
Oh, man, I loved the last interview. We've run it 2 more times since I interviewed before. So we talked in 2023, and I think it's pretty cool that now we get to reflect on what we talked about then. The world is changing. I when I was researching stuff for this interview, I went to your website. I looked at some blogs, and everything was from like 2025. And I'm like, I don't even know if this stuff is even relevant anymore. First, I want to get a brief overview of your company, just for the people who didn't get to listen to the first episode. I want to get a little bit of your story, and then we're gonna delve deep into what we do.
Great, yeah, it'd be a pleasure to. So Real Time started in 2017, based on some research that colleagues and I did at Duke University on robot motion planning, which is how a robot should autonomously decide how to move through the world without hitting stuff. And that sounds like a super easy thing to do. You do that every time you open your fridge and you reach in and you grab a beer. Actually, there are many ways in which you could reach into your fridge and grab a beer where you would hit the fridge or a beer or knock something over, and you don't do any of those, or certainly not after the first beer, maybe after the second or the third. But it's actually quite a complex computational problem. And so we invented a technique to be able to do that in real time, which is why the company is called Real Time Robotics. In 2016, we commercialized at the company in 2017. And over the last 9 years, we've been figuring out how to turn that into something that manufacturing can use in order to be able to design work cells semi-automatically. So instead of having a work cell where you've got a robot and work pieces, and a person needs to come in and decide every little detail of how that robot moves through space and how it works on the work piece, we can optimize and automatically design the motion in that work cell so that everything is as fast and automatic as can be, and we can do that in minutes instead of the weeks or months that it would take a robot engineer to do it. So, and it's been a long journey. It's been, going from the basic science, the basic technology being available and working in the lab, to actually getting to deploy it on real work cells out in major automotive companies, which is what is happening now.
When we were talking in 2023, you really hadn't totally gotten penetrated nearly as much as now.
It took a long time to penetrate because it's a complex industry, and in some senses it's conservative, for good reason. It's I put my kids in my car and drive them around. So yes, everything has to work, and they're a bit resistant to change. But finally we figured out the right way to integrate into their very complex systems, and I think also some urgency came from the side of the automotives. I think they realize the change is coming, and if they don't adapt quickly in the next few years, then they're going to be overrun. And so finally we've broken through. We have our product working on, I can't say which ones, but we have our product working on the manufacturing lines of major automotives that you've heard of and whose cars you may have driven. And it's being deployed and actually used today, which is super exciting.
It's amazing. Are these companies all in the US, these customers?
We're talking to customers globally. Every large car company, you can think of, we have spoken to. I can't say exactly which ones we're in the factories of, but we are in some large ones.
And yeah, recently I've heard several things that say China is just way faster than we are with robots. I mean, we're scared of robots here. Americans are more scared of AI too. And in China, it's like, in other places in Asia, it's like, yeah, bring on the robots. We want more. I want them to do everything for me. And here, the general public, I think, are still scared of it. So my question is, have you penetrated that market, or are Chinese factories still just wanting stuff made by the Chinese?
No, I think, let's say Western automakers, I think, realize the urgency of this. I think it's not quite as simple a question as not quite as simple a question as use robots or don't use robots. For example, even very traditional American automakers have a lot of robots in their line.
Sure.
It's really just about, and you don't even need to think about expanding the number of things that are done by robots. It's just the things that are done by robots have 20 or 30 years worth of delayed, 30 years worth of kind of technical legacy built into them, right? The way that robots are being used is the same way they were used 30 years ago, because those plants were designed 30 years ago. And you've got standard big company stuff happening where there's resistance to changing the way that they're applied. And China has the advantage of being able to build all these things from scratch today. And so obviously they get a much more agile, much cleaner system. And I think,
and the government can just go, guys, you're doing this. I don't care what you say.
Here's X billion dollars. Please make it happen. That's right. That's right. And so actually, I'm not sure so much about nervousness about using robots. I actually don't think necessarily what's done by the robots needs to change very much, although I think in the long run it will. I think it's about, this kind of classic Chinese, completely vertically integrated system where everything works together and everyone lives in the same company and it's all very agile and was built yesterday, and so was designed very cleanly using all the lessons that the West and Japan have learned over the last 50 years. They just get to jump straight to the new clean cool thing.
Right.
And that's part of it. And I think part of it is just also just standard big company stuff. You've been running things for a long time one way, and it's harder to change something than it is to design it from scratch in many cases.
Right. I can totally see that.
I think you're right, though. There is a cultural, there's a kind of AI and automation first mindset coming out of China that is instructive, and actually we can learn a lot from that, I think.
I was listening to this podcast today, and they were talking about how, they do parades and they have like robotic dogs. Mm-hmm. And
that's right.
They're just bring it on. And the same thing with AI, where over 50% of Americans are like not into AI, suspicious of AI. And China, I don't know if it's the people that really are, or if it's the government that they don't really give people a choice, or in the government, they believe they're taking a bet on it over there that, that could solve their problems as far as population. And, it's a big risk everywhere, Europe, even here.
I think there's a couple ways to think about it. I think one way to think about it is, they are, even though they're a behemoth, they're still an underdog, and they're trying to catch up. And so when you're in that mindset, every new technology is an opportunity.
Yes.
Whereas when you are the country that is currently in the lead or doing very well, or where people feel like they're not threatened by other countries, the question is really, is this going to disturb my quality of life? Is it going to shake things up? I'm happy as things are, or I'm not happy as the way things are, but I think this will make my life worse.
That's true.
That's not the same question as we want to catch up to the Americans. What do we have to do to make that happen? And this is an opportunity, and we're going to seize it because things need to change, and changing them will win for us rather than potentially make our lives worse. I think there's also something to be said about the mix of governance and technological advancement and where people feel their lives are at. And I think right now in the US, and this is true more of the US than other places, I think people feel a little suspicious of the combination of big tech developing these things and releasing them maybe before they're a bit ready, and government's ability to think about how to construct policy that deals with this well. And I don't know the answer to that. I don't know how to think about people or how to organize them, but there are people who do, and I think
people who say
there's people who say they do. That's right, actually do. But I think we are in the process of developing frameworks for thinking about, I have this great graph that I like to show my students, which is if you look at the Industrial Revolution which happened in England, right? And you look at, there were actually two of them, but you can sort of look at them as one thing. And if you look at the average height of an Englishman, you've got graphs of the average height of an Englishman. Sometimes they're the average height of an English soldier or the average height of an English.
Average height?
Yeah. So height's a good proxy for health, right?
Okay.
Because health and nutrition, because height is partly genetically determined, but it's partly determined by how good your nutrition is and how good your living conditions are at childhood. And so it's a proxy measure for how good these people's lives were when they were kids. it's not a perfect proxy measure, but it's a reasonable one. And what you see is at the beginning of that industrial revolution, it goes down because you had people who were living in rural areas coming to the cities to get work, but they were living in not great conditions. They were not eating properly. It goes down for a little bit, and then it goes up, and then it keeps going up, and it goes up for like from then until now. And so, one way to think about that is there is an initial hit from this adoption of this new technology, and then there's the benefits which accrue all through subsequent time. And when the Industrial Revolution happened, it was not a thinkable thing that we could have policy that cushioned the initial hit and accelerated the eventual payoff, because nobody knew that was going to happen. They just let it happen and observe the consequences many decades later. But we could, in principle, enact public policy that would cushion that initial bump, that initial hit, and make the win come faster and last longer.
We're already getting to the philosophical part of the conversation. We haven't even gotten to the beer.
When the company, such as Graf Pinkert, knows both the buyer and the seller, it was a fit, a great fit. And that made all the difference in the world, because they knew our desires and they knew the company purchasing KMY. They knew that they were looking, and they put the two together just perfectly. You've been in the business all these years, know and have a great wealth of knowledge of your customers. That was very, very helpful.
Again, literally yesterday, I was listening to a podcast about humanoid robots, and somebody brought up how the Industrial Revolution was responsible for slavery. Now we look back on slavery and we go, man, I can't believe, that we were doing that. And he says, in 20 years, we could be looking at people, they're going to look at people working in factories and go, what, really? People worked in factories? What's going on?
Yeah, I think, I have a strong core belief that technology in the long run makes people's lives better. It's the short run where weirdness happens, while as a society you adjust to it. I think in the long run it's almost always been good. That's why I'm a technologist. That's why I work on developing these things.
I think people would be curious how you got into this. What's your background? Give me the 5-minute bio.
Sure. So I grew up in Johannesburg, South Africa. I discovered programming when I was a teenager and thought this was the coolest thing. And this was the mid '90s, right? So a while ago, you got a copy of a programming language on a disk. You installed it on your computer.
You're the same age as me now. You're 46.
Yes.
Okay.
Yep.
Go on.
And I just loved it. I thought it was the most amazing thing. First of all, that you could program these computers, which before that were only good for playing games. But also that you got to understand how they work. So I learned to program about 1995.
Okay.
It was DOS and 640K of RAM and little tiny programming environments that fit on one floppy disk, so less than a megabyte for the programming environment. But I loved it. I loved programming. I thought it was amazing, and I decided I wanted to do computer science at university. So I got into the good university in my hometown for computer science. And then when I went into computer science, I read about the subfields of it, and I learned about AI, and I thought, wow, that sounds really cool. That could be really fantastic. It'd be really great to understand how intelligence works and how that's a computation, or at least well modeled by a computation. And so I did a lot of reading about that, and I decided at the time that none of that stuff was going to work, which was great, because that's the time you go into something, right, where it was obviously important, but circa 1998 AI, we did not have good answers to any of the questions. And the field had some cool ideas, but they were way early to be usable. And so I thought, okay, I'll study this. I'll focus on this. And inside that, I found robotics.
That's really interesting that you said, well, this seems to be going nowhere, so that's what I want to do. So you the way you put it is sort of strange. It sounds to me like you said, this is going nowhere the way it is. I think it could go somewhere. So you mean you wanted to take a contrarian path? Is that what you're saying?
No, it's not quite that. it's when you want to be a scientist, what you want is you want a really important question that no one knows how to answer yet, or where the current answers are currently obviously wrong. That's maybe different from if you wanted to go into something professionally, right? But I wanted to be a scientist. And so I thought, great, there's obviously huge discoveries to be made here because this is important, but no one has the right answer. It's like if you went into making combustion engines, but we've been making them for a century and they're all already amazing. There's limited scope for new innovation. But if you go into, I don't know, quantum ion engines or something, I'm making this up, but no one knows how to do that yet. But when we know how to do that, we know that it'll change everything. That's what you want to do. You want to find the thing where there's a big gap between the importance of the thing and how good we are at currently doing it. So you can be the one who goes and does the invention. That's when you're a scientist, not necessarily if you want to do it professionally. If you just wanted to be a software engineer or something, you'd pick something where the applicability was more obvious and was closer to usable. But when you want to be a scientist, you want to pick something where the big wins are far away but are very important.
As long as people will value you and give you a little bit of money. And
yes, eventually, yeah. So I guess it was a bit contrarian. I mean, I liked the way that people had been thinking about AI, but it was clear that they hadn't found the thing. The thing was not there yet that was going to cause the breakthrough. And I read a lot of this stuff, and I decided that I wanted to focus on robotics because I thought, well, I want to understand how an intelligence works, and humans are robots much more than they're computers. They're whole bodies. They interact with the world. There's only ever brains inside skulls controlling bodies. And if you want to build a complete thing, you should think about what makes a complete intelligence. And a complete intelligence is always embedded inside a body. There's no disembodied brains in the world. And so
robotics was like
the way to do that.
Early on, you said, I want to deal with not just the brain, but the body
as well. Yeah, that's right. Yeah, because that's the only way you get a complete system, right? And so I got a scholarship to go to the UK. I did a master's degree in AI at Edinburgh. Then I came to the US to do a PhD with Andy Bartow, who won the Turing Award a couple of years ago because he was one of the co-inventors of reinforcement learning. And I wanted to do reinforcement learning. It was the type of machine learning that made sense for robots. So I did a PhD there.
Tell people the Turing test for the people who don't know off the top of their head. Or the Turing Award.
The Turing Award, yes. The Turing Award is like the Nobel Prize of computer science. It's like the highest thing you can be awarded as a computer scientist. It's named after Turing because he invented computer science, more or less. You're really good when they name the award after you, rather than giving you an award, they name a new award after you. Then you've done really well, right?
That's true. I mean, Turing was the code breaker in World War II, and then he basically. The Turing test is just give people a quick example of it. Because I'm sure you can do a better job.
So then we have to reverse a second. Turing did three things, each one of which would have been world-shatteringly brilliant. The first thing was that he invented a formal math model of a computer, and he proved that there were questions that are well answered, that are well formed that a computer cannot answer. So that was like before he even did a PhD, he was 24 something. And in that one paper, he invented all of computer science, and he answered the most important question in it. Like, this is a computer.
This was what, like 1940?
It was like 1930. I forget that. It was in the 30s. And then he participated in the Enigma stuff where he broke Nazi codes and shortened the length of the World War II by about 2 years, probably. And all of that was secret, and we only found out about it later on. And then additionally, in 1951, he more or less invented AI by writing a paper about what it means to think. And in that, and he said that a computer could be thought of as something that thinks. And in that, he invented the Turing test, which is just a test. In the original paper, it's kind of, he didn't mean it as a test that you would pass and then declare that you'd win. It was really like a thought experiment. He said if you couldn't tell the difference between a person and a computer reasonably well in a sort of conversational dialogue game where you were trying to tell which one was a person and a computer, then functionally you should be saying that computer can think. Then we've changed the definition of think from something only humans do to like a behavioral thing, like you can behave as well as a human.
What year
that was 1951.
No, I mean, but what year did it finally come to fruition?
It depends on who you ask. I mean, I think
2020, 2022.
I think there were chatbots that solved it. And I mean, he said it was like a 20-minute test over a text-only thing. People in the early 2010s, we had systems that could do that for some of the time. He only said you needed to fool the human 40% of the time. I think now we can fool the human a lot more than that. But I actually disagree. A lot of people disagree that that's a sufficient test for AI. I think what he was really trying to do was just change the definition of what it meant to be think. He had this analogy between what does it mean to swim? Like, does a submarine swim? And before they were invented submarines, swimming was a thing done by fishes and people and ducks maybe, and it was a very specific physical activity. And then when we got submarines, which swims like none of those things, we sort of generalized the definition to swim to be a more functional definition, like move through water without sinking or something like that. And so what he was trying to do in the paper that introduced the Turing test was he was trying to change the definition of AI away from being a thing that only intelligence, away from being a thing that only humans did by virtue of there being only one kind of animal that can do it, to a functional thing, like the ability to reason and the ability to sort of emit intelligent behavior. And so that's really what he meant by the Turing test. It's a little complicated. Reading the original paper is actually very interesting.
I don't know if this is a nonsensical question or not. But what do you think he would say right now?
I think, geez, it's hard to guess.
Yeah, I know.
I think he'd
curious what you'd say.
I think in some sense he'd be extremely impressed by the progress. I think he would have been surprised that it took this long. All the early AI people thought it was like 5 years away.
Who's the early AI people thought it was 5 years away?
So after Turing, there was a workshop, I think it was 1956 at Dartmouth, where maybe 15 or 20 early people got together and discussed using computers to study intelligence, and that was where the phrase artificial intelligence was first used. And at that Dartmouth workshop, which was really the founding of the field in North America, there was a discussion about how long this is going to take, and everyone thought it was right around the corner. So like
really?
Minsky and Herb Simon and that crowd thought it was. We've got these computers now. I mean, it's in part because they had sort of the wrong guess about which technology was going to be used to solve it. They thought it was going to be a logical inference thing, and we had good logical programs already. And they thought, well, it's just a matter of getting these a bit faster, and then we're done. And of course, they were horribly wrong about almost all of that. But it wasn't an unreasonable first thing to try. It just turned out, in the event, to be not sufficient for what we use now. And the neural network thing was actually present even then. It just was not sufficient then, and it had to go through 2 or 3 revolutions to be able to get to.
What's the neural network thing?
So there's kind of.
I hear it all the time, and my mind is blank now.
Yes, there's sort of 2 at the time, and it's a bit more complicated now. But there were 2 traditions of AI, and one of them was kind of logical and logic based and very formal reasoning. Right, you were going to write down axioms that describe the world using Boolean variables, like it's raining today or it's not raining today. And then you were going to do logical reasoning in the way that sort of Aristotle would have done logical reasoning, or a philosopher does logical reasoning, and say, well, if this is true and this implies this, then this is also true. And you think in this very discrete, logical reasoning way. And then there's another way, which is to say, well, things are a lot more complicated and messy. And so what we're going to do is we're just going to think about, and we're just going to look at how the brain does things. And the brain seems to have these neurons in it, and they're computing these kind of complicated real-valued functions. And so what we're going to do is we're going to build these complicated real-valued function approximators, which is what a neural network is. And we're going to build them in a way that makes them amenable to calculus. So you can take their gradient. And then we're going to use that gradient to do learning. And more or less, that's the whole story of neural networks, right? It really was just the ability to do calculus on a complex collection of interacting computational units. To be able to get closer to the outcome that you see in the data, and you get a big set of data and you train the neural network against that set of data until it reproduces the data, and then you try it on data outside that set and see how well it generalizes, and it turns out it generalizes pretty well. And so that tradition was present already in the 1950s, but we did not have powerful enough computers or large enough data sets. We did not have GPUs, and we did not have some of the algorithms we needed to be able to scale.
Does that have anything to do with the Elon Musk company where the people who can't
you think of Neuralink,
right? Yes. Where the people can type something and then they can move, or that's about connecting computation to your literal brain. So that's about prosthetics, really. That's like a neural prosthetic. What that company's doing.
Um, uh, Neural networks are just inspired by neurons, which are kind of the basic cell that you have in your brain. Your brain is like, to a first order approximation, a giant clump of neurons. And neural networks are like, contain computational simulations that are quite similar to those, not the same and not the physical neurons at all. They're just kind of based on the idea that it's a big network of these things. So they're not really related. The neural networks are just brain inspired in some way. If that makes sense.
Okay, let's go back to just the nitty gritty of the beginning of the interview last time. The beer example. Were you guys sitting around like drinking beer when you came up with this? By the way,
no.
So the idea is that you want to be able to have a robot that can reach inside the fridge and grab a beer and not have it take a zillion years to program and have like the most talented person there. You put in some basic coordinates and it happens. That is that. Did I do an okay summary?
Yeah, that's right. Except I would say two things. One, so this problem is called motion planning, robot motion planning. It's about planning your motions through space. And that problem is as old as I am. So the first motion planning paper was written in 1979 that posed that question. How do you, not specific to the beer example, but just to say, if you've got the robot's in a world, it wants to go somewhere in the world with its end effector or its tool, and it wants to move without hitting things in the world, how should it move? So we didn't invent that problem. Actually, my postdoctoral advisor, Tom Haslazan Perez at MIT, invented that problem. But people had been working on it for decades. And what Dan Soren and I came up with at the time was a way to accelerate solutions to that problem that made them usable in real time. Instead of taking seconds or minutes to find a solution, we could take milliseconds, and that's what made it reusable. But I should say, that was the very beginning of the breakthrough that led to real time. And real time is actually a much more complicated company now than it was then. Right then, it was like we have this one algorithm. But what we've first of all, we don't need our breakthrough was to build a custom processor, and we don't need the custom processor anymore. We can do it in software. We discovered how to do it fast enough in software by using similar ideas to the ones that we invented then. But also we discovered, one of the things that you all know when you're really in industry as opposed to in a lab at a university. When you're in a lab at a university, you solve a nice clean problem with a nice math description, and then you run it on some benchmarks and it wins, and you declare victory and you go home. You publish the graph and you're done. But really, the story of real time is understanding how deeply you need to understand your customers, how deeply you need to go and sit and talk to people who work on the line at automotive companies, not just what they care about, because often they don't have an explicit document saying what they care about or what the internal rules are for getting stuff working. They just have a bunch of dudes who do stuff according to those rules. But also understanding their technology stack, and what does their process looks like, and where are their pain points, and if we solve this problem for them, does it really help them shrink the time it takes to take their cars to market? Because this is one of the major pain points in automotive, right? We discovered actually, and this is how we eventually broke through in part, we discovered that if you look at the time it takes to go from the design of a car to selling the first 100,000 units, it's like 5 years for an American or European automaker. And the fastest Western automaker ever was the Tesla Model 3, which I think it's not exactly this, but it's something like 3 years. And that's because they pre-sold the 100,000 units. But also they got to build their factory from scratch. But Chinese automotives are doing it in 2.5 regularly. And so now and they're doing that because of improvements in it's not that they're using more robots. It's not that they're using less people. It's that the design process of taking the car design and turning it into a factory that produces that car was not efficient. It was very slow in the West and very fast in China, because they would just flood the zone with engineers. They would just start designing the work cell basically as soon as the car sketch was even beginning to come into shape, and accept that they would throw away a lot of work, but try and make it as efficient as possible and accelerate the process.
So it's the same thing as Tesla. They created the factory at the same time that they were creating the car.
Yeah, and if some of that work needed to be redone, they just accepted the cost. They, whereas Western automotives were very sequential. They'd like design the car, get the design right, then they'd start designing the factory, then they iterate on the factory, or design the work cells. And eventually, once we realized that this is where the sort of major bottleneck is, we focused our efforts on saying, okay, we've got this motion planning tool. It's the best in the world by a lot. But that's not enough just on its own. What we really need something that helps these guys automate the design of their work cells, with a production engineer. But obviously, we're not getting rid of the integrators, but hand in hand with the integrators to really drastically accelerate their test and debug cycle, to make it minutes instead of weeks or hours, and to allow them to sort of interact, say, okay, what happens if I move my robot over here? What happens if I use 3 robots instead of 2 robots, or 2 robots instead of 1 robot, or 2 robots instead of 3 robots? Can I drop a robot and get 80% of the time of the performance out? And can I ask that question very quickly, in such a quick way that it's not like you have to guess and then you're committed, that you can just iteratively interact with this.
And this is where the AI comes in, that it makes these calculations?
Well, yeah, this is where our motion planner comes in, and all the technology we've built around it. We've got optimization technology, which is like a physical AI technology that lives inside, that does all these things in a way that doesn't, that isn't approximate, that is exact and performant really fast, and gives you very fast motion out of the robots, but also, can optimize where you place the robots and how many robots you use and all of that stuff.
But do you have to
shrunk that shrunk that slug in the sequence of things they had to do to tiny, right? It just went, and so that takes that off how long it takes them to produce a car. And so instead of, imagine how hard it must be to try and guess what cool cars are going to look like 5 years from now. I mean, it's very tricky to be a company in that situation, to have to make decisions 5 years early about what technology is going to work or not. And we just need to shrink that down. That's what they have to do today. But as they're rolling out the RTR technology, it's just shrinking that timeline by a lot. It's making it faster and cheaper to get those factories up, and it's just reducing their cycle of decision making by a lot.
Well, but we already have these factories up now, so you can't just build it at the same time.
That's right. We can't build the factories from scratch at the same time, but they're retooled for every model. And actually, that's harder than building them from scratch, right? So they face an even harder problem. If you want to go from, one copy of a large SUV to a different new model of the large SUV where things have changed, and you want to retool that factory, now they can do it much faster than they used to do it before, which keeps people working on the line, which makes those things cheaper to sell, those cars, which makes them more responsive because they're more responsive to trends, which makes them be able to turn out new models faster. All of these things, they're sort of clawing back these advantages.
Okay, so you come up with the math and the formula and everything that quote unquote should work. Our audience is in the machining world, and what happens with them is the engineer comes up with, well, this ought to work, this should work, and then it goes on the floor, and then they have to experiment making the part because something changes, the material, the tolerance or whatever. Is this the kind of thing where you put the program in and then you set up all these robots and then you say, go and see if anything crashes into each other and see how it works? Or is it pretty much like you guys come up with the plan and it's so precise that it comes out great? No.
Everyone in real life knows the plan never quite works, right? So the first time. And so automotives go through multiple stages, and one of them is the sort of the design of the work cell, which happens, somewhere in an office, basically, where they design a work cell using a CAD program. And then we do the motion planning. We tell them how much performance to expect. We output a plan, and then that gets shipped to commissioning, where someone local to that thing goes and assembles the work cell with a screwdriver. And of course, it's not exactly the same as the one in the CAD model. That's never going to be exactly the same, right? And of course, the robot works a little differently to the one that you had in the sim. So that you run it, and then it doesn't quite work. You need to adjust it. But with our tools, you can adjust it on the fly and go reprogram, and it sits for a small number of minutes, and then you've got your new thing. Instead of having to bring the whole team over, instead of having to bounce it back to the engineer, very close to where it's being deployed, you can adjust it and maintain it.
This is so interesting, figuring out how they're configuring the factory. Is the process like they have one setup in one factory, and then while they're developing the next thing, they have a different factory that they're changing over, and then that way they don't have like a lull where they can't make cars like between the old model and the new model?
New model. Yeah. So sometimes that's the case. It depends on the automotive manufacturer. We have talked to automotive manufacturers with one factory and ones with tens and tens of factories, and it depends on the manufacturer, right? I would say, and it also depends on the model and what the factory is being used for. You know, some are being used to produce EVs, some are being used to produce large trucks. Very often you'll find that there's a break in production where they actually have scheduled a time where the factory is going to be upgraded for some number of weeks, or they've just scheduled a time for maintenance. Or it turns out that that model that they thought was going to sell a lot of copies sells fewer copies than they expected, and so they actually reduce the number of shifts at the factory so that the factories idle some of the time, right? But mostly the very well-established ones have a fixed number of factories and aren't building that many more. So they have this problem of deciding what gets manufactured where and retooling them. And of course, things got extra complicated in the US. Right now, there's tariffs, and you want to be assembling everything you can in the States. And so that has sort of upended all this stuff. And it just was the case when this happened, the old manual engineering way, deciding to move a factory from, I'm going to pick two random countries, I don't know, Czechoslovakia to New Mexico, and now I'm going to find out there's a factory in Czechoslovakia, New Mexico, but I just made those two up. I just at random. That's not a cheap or easy thing to do in the old way, and with our way, we've drastically accelerated how efficient that is to do. Because your listeners will know the frustration between this nice clicky software application that thinks it has the answer to everything after you say make the plan, and then actually doing the thing in real life. That's not a small gap to breach, but you wish your software could do it. And also how long that cycle is to when you need to change it and send it back to the engineer. That's no fun, right? That's not.
Is this stuff applicable to people like a job shop with 50 employees? I mean, obviously the concept makes sense. You know, yes. We talked before about collaborative robots, and people are using that because robots are dumb, but collaborative robots are lightweight. So if they hit you, you're okay. I mean, is this applicable to the actual people listening to it, or only their customers who are the automotive people?
So I think it will be applicable directly to them, not right at this moment. First, we have bitten off a lot with automotives. We are going to chew all that for a while. I think it is applicable to any design of an automated manufacturing system.
Yeah, I mean, it seems like it.
Yeah, it's just a question of, one of the things I said earlier is we've succeeded finally because we spent so much time deeply understanding the technology stack of automotive manufacturing, of what does it look like for an OEM, how do they interface with an integrator, how do they interface with a robot manufacturer. And that was the trick to making it really work. It's not like a magic solution that you drop in and does it and do everything. And so I think it will eventually be applicable to your guys and many other guys. But at some point, we have to spend the time to actually understand that industry deeply and write the supporting software around that makes it all fit.
And it can work with any brand of robot,
Yeah, we have to go write a driver for every robot that but we're doing that for all the automotives. So every brand and every family within the brand we write a driver for that deals with the specific weirdness of controlling that robot and also characterizing how it moves. Because when you do motion planning with it, you need to understand how it's going to move through space when you give it a command.
This just makes everything super fast compared to what it once was.
Yeah, it's very fast to deploy, and it's we're finding, I mean, if you took a robot integrator and they've got a bunch of guys who are expert at designing the motions, it's hard to beat their performance at how fast the motions are after they've done the work, although we do now. But most of the win comes from matching their performance, but doing it in half an hour instead of, weeks and weeks and weeks. And so really it's about generating very, very performant motions, very efficient motions, but doing that super fast in a way that's in a way that's kind of reliable, right? So one of the questions I often get asked is people say, well, won't an LLM just do this? Can't you just ask a big deep network or can't you ask one of these big generative AI models, won't that just solve motion planning? And the answer is definitely
so
not.
You're saying they're asking the question of, go to ChatGPT or Claude and say, move this arm over here and work with this arm this way. They're asking if that would work.
Yes, that's right. And or a similar technology would work. And the answer is no, because neural networks are approximate always. They are very good at duplicating the data that they have and interpolating or extrapolating beyond that data. And if that data is text and they've got all the text on the internet, then you get good answers coming out. But for a robot, you need to be very performant. You need to perform at the envelope of that robot's performance, which there are no examples of that. So, or very few, way not enough for a neural network to learn from. And you need to be exact. You can't sometimes hit stuff. You can't mostly not hit stuff. You have to always never hit stuff. And so this is why our technology, which is a form of physical intelligence, it's just a different technology family to a neural network. Our stuff works today, it's performant, and it's exact. And those are the requirements, right? You cannot put a robot that 1% of the time crashes on an automotive line, which costs tens of thousands of dollars a minute downtime. You just can't do that. It's just got to be.
But this still has bugs.
Right. Not really, actually. We spent an immense amount of time making sure that it doesn't have bugs. But if there are bugs, they're standard software engineering bugs, right? Like once they happen, you can go in and fix them. With a neural network, if it doesn't do the right thing, you have no recourse other than to try and give it more data and see if that fixes it. It's fundamental to sort of the wave of generative AI tools, that the way that they're constructed is just by learning from example. They don't actually have a way to guarantee that they won't make a mistake in the same way. And so good old-fashioned engineering principles, it should be the case that if the system fails, you can trace where the failure is from and you can understand why that happened, and you can fix it in a way that you assume will generalize to future instances of that same problem. And neural networks don't have that property, but our system does. So even if there is a fault and we haven't had a crash on a line yet, but if there is such a fault, we can go and find out why it happened, and we can make that change. Whereas you can't do that for ChatGPT. If ChatGPT gives the wrong answer, you can say that was the wrong answer, but the mechanism that led it to that wrong answer you can't fix because you don't know what it is.
I'm trying to process the last thing you said, the mechanism that made that mistake.
Yeah, so the thing about a neural network is it's just a big pile of numbers connected with linear algebra, right? That's and we just move those numbers using calculus.
So that's not AI at all. That's just calculus.
Well, that is a complicated philosophical argument that people in the field have all the time. I think it is part of AI, but it's not the whole thing. It's very good at pattern recognition. It's very good at learning, but it is multiple layers of neurons connected through linear algebra, optimized using calculus. And when it's wrong, all that means is some of the numbers somewhere in that soup are wrong. But that's all you get. You get, well, some of the numbers in that soup were probably wrong, and I can do a bit of calculus to make sure it will not be wrong in exactly the same way again. But I cannot explain in a deeper sense why it made that mistake, and I cannot fix it the way that an engineer is used to fixing a problem. Whereas with a standard piece of software, if you wrote some code and, I don't know, the button doesn't click, you can find the piece of code that should have been executing and wasn't, or the piece of code that did execute and shouldn't have been, or the piece of code that executed incorrectly, and you can fix it. But you can't do that with a neural network, right? It's not.
But will LLMs or AI get smart enough that they'll be able to go and identify it and fix it? One can fix the other one?
I don't think so. I think it's inherent in the technology that it's not fixable. It's not fixable in the way you or I think of fixable. It's just the way it was built precludes that. And so I think the generation after neural networks, whatever that is, will have some of the stuff built in. But that's one or two major breakthroughs away at least. Eventually, we'll have an AI where we'll have AI style stuff where you do have built-in explainability, but that's not, the current technology just doesn't support it.
Man, it's a little over my head. I'm somewhat get it.
No, yeah, I was just going to say, but just the way to think about it is, in some ways, Real Time Robotics is an AI, physical AI company, right? We are using technology from AI to to automate these things that were not automated. And in some other ways, you can think of us as a regular engineering company, in that the stuff that we produce is amenable to standard engineering principles, and that's why it's reliable. It's reliable because it was built in code by people who understand the problem deeply and can audit what happens if something goes wrong.
Right. But what they say, of course, is that the AI is going to be as good or better than people at coding eventually, right?
I mean, maybe one day, I think it will be a great, I think today it is a great co-pilot for coding. It is great to have next to you while you write code. And it can generate some code.
Do you use Claude?
I don't
coding?
know. I don't get to write code anymore. No, in my professor job, the programming language I use is math. I write math things, and then my students go write the code. But I think it's great for sort of relatively short. It can accelerate you as a programmer, but constructing, I've gotten how many millions of lines of code that we have written in real time. It's not a small thing. It's an immense product. It could not produce something like that, and won't be able to for decades, I think.
I think you answered this question already, but I was looking back at our interview from before, and you said robots are stupid. Are robots still stupid?
They're getting smarter. They're still stupid in some surprising ways. I think there are now technologies that make them less like obviously catastrophically stupid, right? But we are still in the process of building the basic foundations of physical intelligence, right? Just the idea that it takes a lot of work from engineers so that robots can move around in the world without hitting things is, babies do that. That's not a hard thing to do for a person, or every animal does that. That's basic to physical intelligence. But we are only now understanding the principles that allow us to do that. And so I would say they are still, for the vast majority of real applications, yes, way too stupid to use. But I think in the last couple of years, we've seen enough advances that some of the basic stuff like computer vision is now pretty sophisticated on robots. Like that's beginning to work much better than it ever worked before. And that's crazy impressive. So, and generalizing to new scenarios, like if you put a robot in one room and you ask it to find the door, and you put it in another room to ask it to find the door, it's no longer the case that's brittle. Now that sort of stuff works very well. And that's because of deep learning. But the basic motion planning technology, other than real time, there's very few people that have technology that enable basic movement without smacking into stuff. Is
this the same technology that's going to be used for humanoid robots? And so if you want a cleaning person robot, or
so there's a lot of argument among roboticists about what exactly will work in the end. My guess is, for something like a humanoid robot, you're going to have multiple layers of physical intelligence. And
first,
some of those layers...
define humanoid robot, because I heard it on a podcast. What do I know what it really means? Tell me what you mean.
Typically, people just mean human shaped. So like 2 legs, 2 arms, and hands.
Okay.
There's a couple things going on here. One is it looks like people, so people think it's cool, and okay, fine, C-3PO. The real good argument for it is that the world was designed for humans, by humans, and so if you want to put a robot into the world designed for humans by humans, it should be roughly human-shaped, because we know that humans are able to do all the things that you need to do in the world. So, and also, cupboards are at cupboard height because people are at that high, and desks are at desk height because people sit at about that height, and handles are handle shaped because they're built for human hands. And so you should design your robots to have those physical characteristics, so then they'll fit right into the world, which was designed for roughly human.
Assuming we're not going anywhere, they better adapt to us.
Exactly, that's right. Exactly, and we've adapted the world to us, so they should be that shape. I think the counter argument is that specialized shapes almost always do better than that. So cars aren't human shaped, and they're not horse shaped either. They're, and your dishwasher's not human shaped, even though before dishwashers they were humans washing dishes. Now it's a box, and because we engineered it to be the right shape for its task. And so there's kind of one debate there. but I think but let's take for granted for now. Let's say we want to produce humanoid robots. We want them to be general purpose. I think what is needed is 4 or 5 scientific breakthroughs that understand the nature of the basic intelligence of moving around and interacting with the physical world. I think motion planning, which is the basis of real-time technology, but not the only thing, is part of that. I think computer vision, which is coming from deep learning, is part of that. But there will be several more until they get to the point where they can kind of show up at your house. You can point your dishes a few times and they'll be useful. I think the software technology is not there yet, in my opinion. The hardware is there. The hardware's been there for a long time. And it can look and feel like you're making progress because you can see a robot walking around and think that that's cool. It looks like a person. It's moving like a person. But there's deep questions about the brain that are not resolved and needs to be resolved, because a humanoid robot is a human, right? Like if you can get a generally intelligent humanoid robot, you have solved AI in the maximal hard setting. That's like hard mode, right? It does everything that a human can do. And we're quite far from understanding all of those pieces, I think.
All right, I'm going to ask you to predict the future. I'm sure people ask you to do it all the time and you roll your eyes. This is similar to what we talked about a while ago, is, our people have factories, or are people listening to this work in factories? The last podcast we did, we predicted that wages for talented people in factories are going to go up because, it's just going to be a higher demand for good people. There's going to be people not going into, being a doctor or a lawyer, but they're going to be, maybe a doctor, but, with AI and stuff, it's going to be, a lot of these things are going to be less desirable and people are going to be working in factories. If somebody said, best case, worst case, that's personal. When typical factory, it's pretty much just, you're not going to have too many people in there. Any thoughts? This is what you do. You're doing this right now. So, but
yes,
on a much larger scale.
Yes. Well, that's not quite what we're doing. So we're not changing the number of people working in the factories, and we're actually not even changing what tasks robots are applied to. We just make it much easier to apply robots to the tasks they were already applied to. And I think that will be the case for probably my guess is, in automotive, at least in the next 3 to 5 years, what you'll see factories becoming, the design of factories becoming partly automated, those factories becoming much more responsive and agile. But it won't change what is being done with robots versus with humans. That's much further out. I think.
Well, how far?
I think eventually that'll happen. Eventually, it will be the
10
case
years?
that. I think 10 to 15 is where I would guess when we are starting to take things that people used to do in an automotive manufacturing, and now they're done with robots. That's my guess, and it will happen slowly. I have this rule. I call it like George's rule of automation, which is that much more structured, high value, high volume things get automated first, and less structured, lower value, lower volume things get automated last. And it's actually the structure that's the dominating question. So the more structured and repetitive the thing is, the easier it is to automate. And that's why in car manufacturing, spot welding is automated, but like you need a person to go stick in the cables or whatever. And so what you'll see is it'll just slowly start to expand the things that the level of structure that automation can deal with. It will slowly start to get more and more flexible. That's why in Amazon's warehouses, for example, the thing that got automated first was go and get the box and bring it to the person. Because you just, the box is in a giant grid, you get a grid number, you go pick it up, you bring it to the person, you drop it there, and then a person packs the box, because that's unstructured, because you don't know what's going to be in the tote that you're handed. And so the very structured thing gets automated first, the less structured thing gets automated last. And I think that rule will hold for large scale manufacturing for a while. And so, but then slowly over time, we'll expand what can be done efficiently by a robot and cost effectively by a robot. Will change the ROI, and then they'll slowly start to expand what is automated. But it's not going to be a fast, scary process. I think it's going to be a slow, incremental process, and it's going to bring a lot of value.
If you look back at your predictions, are you usually an underestimator or an overestimator of how, if you look at your track record?
Okay, I would say generally everyone who got into AI before 2015 is a raging optimist, because otherwise it was a weird thing to do with your life before then. Having said that, I think I, along with others, have probably underestimated the pace of change in the last 3 or 4 years. Stuff happened quicker than even we thought it was going to happen. But that happened outside of robotics. And robotics is just harder than everything else, because this interaction with the physical world means you can't just kind of almost do it right. You can't just kind of approximately get the thing right. You have to get it exactly right. It has to fit. Everything has to work great. And that's so much harder in real life than it is like outputting text that's about right. That sentence says about the right thing is much easier than welding exactly in this one spot. And so I think robotics is partly still going to move at the speed of engineering. Or closer to the speed of engineering than other things.
And just going back to what we talked about at the beginning, do you think that these developments are going to happen first in Asia?
It's hard to say. I think they have sort of the advantage of designing these factories early means it's much easier to be a follower than it is to change an established industry. On the other hand, Tesla innovated a ton of this stuff, right? Actually, and actually, I think if I look globally, I would say that the core technical innovation, the really, really fresh new stuff, tends to happen in America. But then what can go wrong is that established industries in America don't follow suit, and someone like China sees that and says, "Oh, that's great, that's amazing technology, we should duplicate that," and then catches up. While America's kind of, like if you look at EVs, right? I mean, the innovation in America created this whole thing. But then it was the case that only a small number of American companies kept going on it, and entire Chinese industries were built around it in the intervening time and have caught up. And so that's the risk, right? The risk is that the genuine creative
and part of it is political
happens in the States. Part of it is political. Yeah, there's a bunch of reasons. I mean, some of it's political.
H-1B visas and, people, money talks,
Yeah, that's right. But it's not just that. It's also like established industries, right? America's been on top for a long time, so its industries are established, so that makes them slow to change. There's lots of reasons.
Which is what you're finding with automotive.
Yeah, although they're changing now. I think they understand the threat, but the risk is always that the sort of innovative genius of America doesn't get capitalized on by America. The spark happens here, and then other places chase it because they have clearer vision, or they're trying to catch up. Often they're behind, and so they can take the risk. So that's my guess. That's my feeling.
Yeah. No. As we wrap this up, people who follow me know that I'm really into serendipity. What's something serendipitous that happened recently or in your life, or something that sticks out, a lucky break, something you've figured out because of something fell into place? It could be your latest discovery. It could be meeting your wife. It could be ending up in this country. I don't know. What's one thing that happened to you?
It's all serendipitous. It's all just extremely unlikely things happening one after the other for me anyway. So my very favorite story, I guess, here is, so in South Africa, when you turn 21, it's a big birthday. So you have a big 21st birthday, and then you have I asked my 21st birthday present is I wanted to go visit America, and I wanted to look at grad schools. I thought I wanted to do a PhD, but I wasn't sure what in. I thought I wanted to do it in AI, but I wasn't fixed on robotics yet. That hadn't occurred to me. So my sister took me to America, and we went to Boston because I wanted to go see MIT. So we went and we saw MIT, and then I wandered into and then I wandered into the MIT bookstore. And my sister, and at the time the exchange rate was, it was very expensive for a South African to go to the US. So my sister was like, "Wow, there's a bookstore. It's full of technical books. You love technical books. You can buy one." And we went to the MIT Press bookstore, and MIT Press is just like, it's like Nirvana for nerds. And I was very excited. So I looked through the whole bookstore, and I found a book on AI robotics. And I remember this very clearly because I was there on December 8th, 2000. And that book's publication date's December 14th, 2000, but it's an MIT Press book. So they had it a couple of days early. So I must have been one of the first few people to buy it. But I bought it and it completely changed my life. I read it and was like, wow, yes, robotics is the thing. We need to do robotics because it integrates all the things from AI into one thing. And I sort of read it on the plane home. And a couple of weeks later, I was like, I want to do a PhD in robotics. That's how I want to, that's what I want to do with my life. And it just hinges on this one selection of one book at that one moment that came out a couple of days early so I could walk into that bookstore.
That is the most amazing case of serendipity. Did you end up going to MIT?
I did my postdoc there, actually. Yeah. So I landed up, but by then the buildings had changed. They'd built a new building and all that stuff. But once a week I'd walk into the MIT bookstore and buy a book because now I can buy as many as I want.
So where did you end up going rather than MIT?
I did my PhD at UMass Amherst because one of the founders of reinforcement learning was there. So, which is Western Massachusetts. Because I also got the reinforcement learning book. I ordered that off Amazon actually and read that and thought, wow, reinforcement learning and robotics, these two things should go together. And so,
that's amazing. That's such an amazing story. Do you have anything else you'd like to say to the people of the world, or is it just mic drop?
No. I'd like to say that I think that, your audience are very real in the sense that they build things, they make things, and they are where the tool hits the workpiece in this economy. And I think that AI, if it's done properly, these physical intelligence tools, if they're the right tools and the right technology, and they understand the audience well, which is what we do at Real Time, are bringing a lot of this stuff back to America or recentering it, and are gonna come with a lot of wins. They shouldn't threaten anyone. But they are gonna make your audience's lives better, make their businesses better. The opportunities are there, they're happening. They'll be slower than you'd think, but they are gonna make all of that stuff better and cooler and faster and happier. And I'm looking forward, hopefully, to working with them one day.
Awesome. Thank you so much. Man, what a great conversation.